Okay, hi. I'm going to do a problem here that is something that will help you with some of your homework, and it's also something you need to do for the course. This is a problem where we're going to look at the EMF that's induced in a loop by a magnetic field that is non-uniform. So let's take a look at the picture. All right, it shows basically that you have a wire, and the wire is going to be carrying a current which goes up towards the top of the page. And of course that wire produces a magnetic field around itself, and then we're going to have a loop over here which is just a loop of wire, and we want to know what EMF is induced in that loop by the magnetic flux that's passing through it. So of course in order to have the EMF you have to have a change in flux, and so we're going to solve the problem assuming that the current in this wire is steadily increasing. So as the current gets stronger, the flux through the loop should get greater and greater. And so that's where the change is going to come from that we need to induce the EMF. So before we get into the math of it, let's just think about this. If you have a wire and you use your right-hand rule, you can predict the direction of the magnetic field. So near the wire, the magnetic field is going to be directed inwards. So this is B, and it's going to be quite strong. So maybe take a second, use your right hand, put your thumb in the direction of the current in the wire, and then your fingers will poke into the page on the right side of the wire. And so that's going to tell you that the field goes that way into the page. Now, as you get further from the wire, the field gets weaker. So maybe over here the field is actually smaller. And so this is a non-uniform magnetic field. Okay, it's not steady, it's not equal in all places, but it's getting weaker and weaker. And of course, as you go further out, it just keeps getting smaller and smaller. Okay, so that's what makes this problem a little bit trickier. Okay. So let's walk through the steps here. First of all, let's figure out and let's remember the expression for the magnetic field when you are near a long straight wire. And I said you should know this because you really should. That expression is going to be the field is equal to our constants multiplied by current divided by the distance from the wire. Okay, so R is basically going to be the distance from the wire to any point on the right side of the loop. Okay, so this is going to be important. We need to assume this as our starting point. Okay, next thing we want to do is to find an expression for the magnetic flux through the loop, because again, we're going to be using Faraday's law, so we need to know the flux. So this is not going to be something where we can just take B times A. I'll write that, but I'm going to put a line through it because we can't do that because the B is not uniform. So it's not that simple. And so what we're going to do is actually figure out the flux that happens inside of a wedge. I should say a very narrow, skinny rectangle. Okay, we're going to look at the flux that happens inside there, and we're going to basically do an integral to add up the flux across the whole inside of that rectangle. Okay, so we would say in that case that the magnetic flux that passes through that can be written as the magnetic field times the area of that thin strip. Okay, so let's just make sure we understand that. So L is going to be the vertical height of my loop. My dr is going to be the width of this strip, this small area. And because it's a very small area, in fact it's calculus small, or the thickness is calculus small, we can make the approximation there that the magnetic field is going to be just a constant value. And that's important because now we're just looking at a really narrow area, which is parallel to the wire. So at this point, I can actually substitute for B the expression that's up above. And it's okay because I'm not really, the radius isn't really changing yet. It's kind of a fixed radius R, and it's a very narrow slice. So that allows me to do this substitution here for B. Okay. Now, if you think about it, what if I made my slice go the other way? What if my slice was perpendicular to the wire? Could we still do this? And of course, the answer is no, because that would defeat the whole purpose. If you made your slice go like sideways in this picture, well, the magnetic field would be changing along the whole length of that strip. So it's very important that the strip that you choose has to be parallel to the wire, right? Because you want to make the assumption that the magnetic field is constant there within the strip. Okay, so then what we want to do next is find the total flux in the loop, and that's going to be given by the integral of the flux through one of those strips. And so what I do is just substitute in, and I can immediately pull out a lot of things which are constant, such as the current, of course this stuff, and then the current I can pull out. Of course I can also pull out L, that's a constant. But my 1 over R, right, is not a constant, and that has to stay in the integral, okay, because this becomes an integral of dr. And what I want to do is I want to integrate from A to B. A is going to be, let's go back to the picture, A is the inside radius, B is the outside radius of the loop. So that's the integral I need to do. All right. Now this integral is the natural log, and if you do those endpoints, this turns out to be the natural log of the quotient. And I hope you can kind of demonstrate that to yourself, because it's the natural log of B minus the natural log of A, that becomes the quotient. Okay, so that's the magnetic flux through the loop. Okay, so then we are just about done here. The last step is going to be to find the magnitude of the EMF. So I want to take the derivative, the time derivative of the expression I have up here. Okay, and that's going to give me that. So then you kind of look and you see which one of these things inside here is changing with time. And going back to the original problem, we said there's only one thing here that's changing with time, and that is the current. We said it was increasing. So everything else comes out front, and what you end up with is going to be all that stuff times the derivative di dt. And that would be the expression then that you end up with. Okay, so we can't really do any more with it at this point. Obviously, if you wanted to calculate this, you would need to know the length. You'd need to know A and B. But more importantly, you would need to know I and the function for I. To, how does it vary with time? So as an example, I'm not going to do this, but if you could say maybe the current is growing in kind of an exponential way, where it starts off with some value, I'll make it something like that. That kind of looks like our capacitor charging formula. So this would be an example of a current where the current would be doing this sort of thing, approaching an asymptote. And so, the next step in this problem would be for you to take that expression and take the derivative of it and then plug it back in here and multiply it by this, and then you could actually evaluate the EMF. But I'm not going to do that in this video. I just want to show you how to set that up. So this is just an example right here. All right, and then that's pretty much it. Oh, we should probably figure out the direction of the induced current to make this complete. I'll let you guys do that. You can check it out. The direction would be counterclockwise, and you can show that either through Faraday's law or through Lenz's law. And that's something that I'll let you ponder a little bit, is why that turns out to be a counterclockwise current in the loop. Okay, so hopefully that helps. This gives you the overall technique. And again, just to recap, the whole newness of this problem is the idea that the field is not uniform. For that reason, you have to do an integration to find the overall flux, and you have to be clever about it and make your integration such that every element of the integration is parallel to the wire, where in other words, the magnetic field is constant. Okay, so the idea here is that B is constant along a vertical strip, and that is the key to solving this problem. Good luck.